Hello, everybody. My name is Zach Lefke, and I'll be presenting today on the Prototype Virginia Ground Station Network that we established as part of something called the VCC mission. I'm going to go ahead and apologize up front. I have to move very quickly through these slides to fit them all in a 15-minute window. I might even may even skip through some of them. If there's something not covered in the slide deck or the associated paper, please feel free to reach out if there's any interest, and to my email address there listed on the title slide. And with that, I'm going to go ahead and kind of breeze through. So this is me. I'm a member of research faculty that works for a group called the Hume Center for National Security and Technology at VT. There's a lot I could say here, but there are the details. On a good day, the important part is I like building antennas and I like ground station networks. I've been doing it since I was in the Marines prior to coming back to VT, and I love the work. So I'll start this presentation with an overview of the VCC mission, which is a big driver for the network. Hopefully spend most of the time talking about the network itself, and then go over some regulatory coordination and scheduling information and sort of the requirements associated with that, and then finish up with the conclusions and future work. So I keep mentioning the VCC mission. What is that? So the Virginia CubeSat constellation is a collaborative program kind of across the Commonwealth of Virginia. It's led by the Virginia Space Grant Consortium with Mary Sandy, the director of VSGC, as the PI for the VCC mission. It's funded by the NASA USIP program, and it's part of the launch was provided through the CSLI program. It's 3 1U CubeSats, one built at each the universities listed there, UVA, ODU, and VT. Hampton University is also involved for mission data analysis. The kind of key takeaway, the important point of VCC was educating students, getting undergraduates involved from concept to on-orbit operations for a small sat mission. So that was the number one mission objective. Currently to date, over 160 undergrads have been engaged. They did have help from graduate students and research faculty and academic faculty. However, it is a very heavily undergraduate-led effort. They were responsible for all the design reviews, for the actual assembly, fabrication, PCB layout, testing, breaking, fixing, retesting. All of that was handled predominantly by undergraduates. So we're really happy about that. There was a science objective as well related to atmospheric drag modeling. They deployed to orbit on July 3rd, almost exactly a year ago, July 3rd, 2019. And it was a very highly collaborative mission in general. I list VT, UVA, and ODU there, but really that should also include VSGC, Johnson Space Center. Wallops Flight Facility provided a massive amount of support, and a number of other groups. So very, very collaborative in nature, and that high level of collaboration is what really enabled or made the network possible. Everybody working together to get it done and get the mission done. So that was fantastic. This is a quick snapshot of all the team members involved. It's loosely, or not all the team members involved, a small snapshot of the team members involved. 160 undergrads right there. Couldn't fit them all on one page. So this is the team as it kind of stood around sort of integration and into launch and early operations, or deployment and early operations. So it's loosely VT to the left, ODU kind of in the center, UVA to the right. Mary Sandy, the VSGC PI, is down in the bottom right. And the 3 team leads from each university are shown there in the top center. So the overall communications are what you would kind of typically expect from a university small sat mission or an educational mission. 9600 baud, GMSK, using the AX25 protocol. We operate in the 401 megahertz satellite service or satellite band, which I'll talk a little bit more about here in a minute. Each university has its own ground station, and it was responsible in the sort of initial concept. The mission operations would be left up to each university. There were a lot of design freedoms in the individual spacecraft, but we made sure we weren't doing anything that would conflict with the overall mission objectives. And then the operations are going to be left up to the individual universities. There were some changes that happened that kind of facilitated the creation of the network. But the original concept had each university operating its own spacecraft. And because of that, there were individual FCC licenses, which are kind of the information's called out in the chart or the table on the right. So each university, again, has its own ground station. This is kind of the high-level overview. They're all pretty much similar in design, with one notable difference, which I'll cover in this slide. again, I apologize, I'm moving quick here. But something happened about midway through the mission where originally we were going to operate in the amateur satellite service in the UHF band up around 436-ish megahertz. However, a decision was made to reband down to the 401 megahertz spectrum. Unfortunately, the byproduct of that was that ODU and UVA had already procured equipment specifically for the amateur satellite service and couldn't afford to sort of upgrade and add a 401 megahertz dedicated system to their ground stations. So instead, they elected to sort of physically modify their equipment to perform and to operate in the 401 megahertz spectrum. VT, on the other hand, we had an amateur antenna system and RF front end and all of that, but we were using it for other operations, so we couldn't actually reband our system. So instead, thankfully through support with the AOE department, we obtained a dedicated 401 megahertz system. And all of this led to kind of a key reason why we started the ground station network, or actually did the ground station network and implemented it, is that the modifications that ODU and UVA did led to a number of communications issues with our ground stations. But because VT had the dedicated 401 system, it operated a lot smoother and things went a lot better with the communication side of things. So there was a sort of desire that while we're troubleshooting the ODU and UVA issues, we want to continue on with operations. And so if we could route commands over the VT ground station, that would be great. And so that's what kind of drove the development of the ground station network. With that, I'll get into more of the details here. So this is the high-level overview of what the network provides. So it's a virtual private network that connects all of the tracking stations to all of the operations centers. There's also the connection to the Wallops Flight Facility, which I'll talk more about in a little bit. And the sort of thing to call out that's maybe the important takeaway is that blue line showing UVA communicating through the Virginia Tech ground station to the UVA spacecraft. So the important point here is this is actually how UVA established communications with their spacecraft. So as I mentioned, they were having some issues with their tracking station during the early operations of the mission. And so while they were working on that in parallel, we were able to actually establish communications with UVA's spacecraft, but it's through the Virginia Tech ground station. And that just further highlights the collaborative nature of the mission and how well everybody worked together to make this happen. Unfortunately, the ODU and VT spacecraft never called home. We still haven't gotten any responses out of them. And as part of the troubleshooting effort for that, we were granted access to the Wallops Flight Facility 18-meter ground station. And so that's what's kind of depicted with the VT mission operations attempting to communicate with the VT spacecraft via the 18-meter antenna system. Unfortunately, we haven't heard from them yet. We'll continue to try to talk to them. It's been about a year, but they'll be in orbit for, VT at least will be in orbit for at least around 5 years. ODU has a drag brake, so they'll burn up fairly soon. But we'll continue to try to establish communications with them as time rolls on. So this just gives a high-level overview of the breakdown of the protocols involved as a function of the OSI model. This is a more detailed view of that. Again, I would go into more detail, but I just don't have the time for it. The important thing to call out here, though, is related to the security of the mission. So each spacecraft uses a command authentication mechanism that has specific encryption keys associated with that. And we did not want to have to require that a university give up its encryption keys to another university as part of their mission. That maybe would have been okay for the VCC mission with how collaborative everything was, but generally that shouldn't be a requirement of the network in general. We plan to use this network for future missions as well. So at no time should any spacecraft owner be required to give up the authentication keys to their spacecraft to some entity outside of their control. So that was very important with how we segmented and sort of layered the operations and fit that in. And it kind of drove some of the design decisions. The other major reason that it's broken down like this is how it actually worked anyway. The Mission Operations Center C2 software communicated with the tracking stations over TCP/IP connections using KISS and AX25 and all of that. So it wasn't really that hard to stand this up. We just had to provide the connectivity over a secure connection, which is why we use a VPN. This is just another view of the OSI breakdown. So this is how we stood up the VPN connection. All of this is running on VT ground station equipment. And the way we've established this for this mission and other missions is what I call a Docker space. It's just a term we use that indicates a collection of Docker containers that are performing specific operations for specific missions. So we have multiple Docker spaces running This is depicting kind of a subset of what we're running for the VCC mission for operations. So there's another Docker space, for example, for the mission data warehouse that would contain all the functionality for the database and the mission science data storage and all of that. The important thing to mention here, so in addition to running all of these things in kind of isolated Docker containers, where each mission is isolated from other missions, this is where we actually run the VPN server. So all of the tracking stations and operation centers have their own credentials that are maintained by VT and the OpenVPN server for that Docker space, but distributed to each university. They connect over that secure VPN or connect to that VPN, which then allows them to reach out to a different IP endpoint on the VPN that's associated with each one of the tracking stations, including the Wallops interface. So Wallops shows up as just another IP on the network that they can route their traffic through and kind of point their command and control software to. And so this shows how that breaks out. And really what's running in that Wallops interface is a GNU radio flow graph that does some signal processing, which is shown here on this slide. Again, I apologize, I'm moving quick, but I got to get through all of this in a short amount of time. So basically, for those familiar with the Wallops 18-meter dish, they have something, a new software radio framework that currently doesn't support, or at least at the time of our operations, it may by the time that I'm making this deck, did not support the AX25 protocol. So what that meant was we had to do some additional pre-processing that we don't do when we're communicating with the normal university tracking stations. And that's really because all of this functionality is already contained in the individual university flow graphs that's running at the tracking stations. So we had to do some kind of, where I show mission operations breakdown, this is really only for the university to university interface. Where that line is drawn for the Wallops interface is actually a little bit lower down into the physical layer. And that's sort of called out in detail here. So we get down all the way to the burst scrambling, which is a bit level operation. And then we send that out to Wallops. They do the uplink, then they do the downlink, and then we get that data back and then route that back out to the client, which in this case is whichever university is connected. So again, all of this is what's running in that Docker container for the Wallops interface. This shows kind of a very simple overview of how the Wallops processing actually works. So they do support a number of the physical layer operations that have to happen, like the NRZI encoding and decoding, the GMSK modulation, all of that. That's about it for how the Wallops interface works. Let's see, I've got about 2 minutes to finish up, so I'll kind of breeze through the remaining sections of the deck here so I can make sure I get to the conclusions. So again, originally each university was going to be responsible for operating its own spacecraft. However, in order to stay legal, each university ground station had to have an authorization to transmit on the other university's frequencies. So that's kind of depicted graphically here. We got special temporary authorizations. Whenever we operate through Wallops, I should also mention that we don't use an FCC license for that. We obtained NTIA authorization through the frequency managers at Wallops who ran that up and got the approvals for us to operate through their system. So now that we can do it, how do we do it, right? So a lot of planning and coordinating has to be done in order to support the communications, and I only have a minute and a half to finish here, so I'll move quick. So three satellites, 4 ground stations, lots of different ways we could route the traffic and do the commanding. So this is kind of what it looks like. This is the overall flow. So we run an SDK simulation, run that through some Python scripts that gives us what we call a network schedule. We then have to send that schedule, because we're operating in the 401 megahertz band. There's a potential interference problem with the International Space Station. So we send that network schedule over to the Johnson Space Center for coordination. They basically redline any pass that would potentially provide an interference problem to ISS, and then they return that sort of approved schedule to us, where we know what passes we're explicitly not allowed to operate. Any other pass that they don't redline, we're allowed to operate. We also have a schedule from Wallops Flight Facility. As one might imagine, they operate multiple spacecraft. So we figure out where we fit on their schedule, what we're approved to do from JSC, do an internal coordination, request our passes from Wallops. We get a final approved schedule. We actually execute the pass, which is the fun one. Then we send a post report, and sometimes we analyze the collected data. That's also pretty fun. This is kind of what the coordinated schedules look like. I've got 12 seconds to finish. So a lot of future work. I talk about it more in the paper. 7 seconds here. acknowledgments to folks, useful links that might be helpful. And with that, I'm done.